Okay, so now we'll be, you can say, starting our next major topic, which is recurrent neural networks, right? It's a pretty detailed topic, so I'm expecting that we'll be spending maybe next 3 weeks on this topic. Of course, not only on RNN, but some of the allied topics or some of the advanced concepts that are related to recurrent neural network, right? And the key idea that we will be discussing is sequence modeling, right? That now we will be dealing with sequences. What are sequences? I will formally tell you in a while, right? But how is it different from CNN? That in CNN, you give an image, you have the prediction. You give an image of cat, it says there's a cat or a dog or whatever is present, right? So it's like one shot. You give something, you get the output. On the other hand, now we are talking about sequence. Maybe if I'm talking, so it is a sequence of words, right? When you are reading a book, it's a sequence of word. When you are speaking, your signal is like a sequence. Okay, so just keep that in mind, and then we formally I tell you what actually we mean by sequence. So for this particular discussion, we'll be, you can say, first looking at what do we mean by sequence modeling and how conventional ANN or CNN cannot handle sequential data, right? So we'll do a comparison of a conventional network and a recurrent network, right? And then we'll design some very simple vanilla RNNs. Then we'll see what are the problems with vanilla RNNs like vanishing and exploding gradient before moving to the advanced topic for the next week, which are LSTM and related, you can say, architectures. Okay. So when we say sequence model, so either the input or the output or both of these are sequences, right? So what does that mean? There are different examples in which either input is a sequence or output is a sequence or both input and output are sequences, right? So let's see these examples one by one. The first example is speech recognition. You have an input which is a sequence. You give it to model and we expect the model to produce the transcription, which is again a sequence of words. So in this case, the input and output are sequences, right? Then you can make a model which can generate music for you. So the input can be empty set, nothing, or it can be the type of music that you want, classic music or modern music or anything. And the output is sequence, which is actually, you can say, a computer generated music, which you can listen to. Then again, a very classical problem, sentiment classification. You have a review and you have to predict whether it is positive, 1 star, 2 star, or 5 star, right? So in this case, input is a sequence of word and output is a single value. Output would be 1, 2, 3, 4, or 5, any one of these, right? So in this case, output is not a sequence, only input is sequence, right? Then you have again DNA analysis where you have a sequence and you have to identify a subsequence within that. So again, a sequence to sequence matching problem. A very common application that we'll also see is machine translation. You have a sentence in one language, right? Maybe in French, and you want that corresponding translation in another language. So both input and output are sequences, and the length of these sequences can also be different, right? If the sentence in French is 10 words, in English it can be 8 words or 12 words, right? It is not necessary that you will get exactly 10 words in a different language, right? Another problem, video activity recognition, where the input is a sequence of frames, frame 1, 2, 3, and so on. And you have to tell what is the activity. It's a verb like running or eating or sleeping or whatever is going on, right? And then the last one, which we'll see in our discussion, named entity recognition, which we discussed a little while back as well, that maybe we have to find the names of people in a sentence or names of places, or you can say names of organizations, right? Because these are things you don't find in a dictionary. So you need to apply NLP based techniques because it is important to identify name of the people, right? So again, here the input is a sequence and output is also a sequence where we expect a one at all the locations where we find name of a person and we expect a zero elsewhere. Okay. Now let's see that what if we try to solve these problems with the traditional ANN, right? That you feed an input and you expect the output, right? Now, why this will not work, we'll discuss it many times, right? But let's take a simple example. When you are dealing with a simple ANN or even a CNN, okay, this applies to a CNN as well. The problem is that your output are not dependent. Now, what does it mean? If it is a classifier which can recognize animals, if I feed it with an image of an elephant, it will say it's an elephant. If I feed it with the image of a dog, it will say it's a dog, right? if I change the order of these images, it will first say dog and then say elephant, right? So you see, it is not dependent on the order in which you are presenting data to it. You can present it one image, it will take decision for that image. It is not considering what was before that or what is coming after that, okay, because it is not trained that way. So rather than images, it means if I am feeding it with words, suppose I feed it with, say, the movie was good. Okay, so now you are feeding one word, okay, but you have a label that it is a positive review, maybe 5 stars for this whole thing. Okay, you cannot have a label only for the word the movie was good. When you feed the complete sentence, only then you can tell that okay, it's a 5 star rating. Okay, but in this conventional architecture, we don't have any way of feeding sequential data. Whatever we feed, it is totally independent of whatever we fed previously or whatever we'll be feeding next, right? So now if you also compare it with the humans, right? So you see, when when you are reading this text which is on your slide, okay, so when you read something, it makes sense to you because in your brain you are keeping track of what you read previously. Mean you keep it temporarily in your buffer, that okay, I'm reading this, and then when you need read the next word, you combine the information you had previously with the next word, and as a whole it makes sense to you. If you read one word and then throw it away, then you read the next word out of context, then you see you will not be able to make any sense out of the text, whether you are reading or you are listening, right? So in other words, our thoughts have some sort of memory where you are keeping, although it's like a buffer where you are for a short time you are holding something in your brain, and then when you see the next you can say data, you combine previous information with the current information, and as a whole you make sense that what is being talked about, right? Now, since this is missing in ANN, so we'll be moving to RNN. How RNN will handle that, will be gradually moving towards that. But now let's see a few of the examples that we'll be discussing as case studied in our discussion. So the classical example, as I told you earlier, is sentiment classification, right? Where input is a sequence and output is a class label. It can be binary, positive or negative, or it can be a rating, right? So this is an example that we'll be doing. We'll also be implementing this. Then this, you might remember in the beginning of the semester, I had shown you this. So now we'll also be discussing it in detail, which is image captioning problem, where input is not a sequence, it is a single image. And output is a description of an image, which is a sequence of word, right? So you see, we feed this image, which is a single image, and the output is a sequence of words. And for every image, this length of the sequence is different, right? You don't know in advance that how many words would be there. Another application that we'll study relatively in detail is language translation, where you give a sequence of word and you expect another sequence of word. So it is sequence input, sequence output, but length of input and output can be different, right? So now let's come back to how we'll be using recurrent neural networks and why we are not using ANN. So this is actually the summary of what we already studied with some case studies, that um, to ANN or even to CNN, you feed one sample and you get one output, right? Means you cannot feed sequential data. Even if you feed it, it will be taking decisions independently, right? It will not be memorizing that what decision it took for the previous example and taking that into account, it takes the decision for the next example, right? Because ANNs do not have memory and they have a fixed architecture. Fixed architecture means that you have seen in the previous case studies that sometimes the length of sequence can vary. So you see ANNs have fixed number of neurons, so they will not be able to deal with a different lengths, because every time you have to produce an output, sometimes there are 3 words, sometimes there are 5 words, 10 words, right? So this would be a challenge. And most importantly, biologically, RNNs are more realistic, because just like brain, RNNs have some sort of memory, that when you are taking some decision, you are also taking some information from some past data, right? Okay, so again, uh, let's see one more case study, that if we try to solve the captioning problem, right, image captioning problem, then what actually will happen with if we try to solve it with a conventional ANN, right? So input you don't have a problem. You can feed the image to it, right? If the image has 100 pixels, you will have 100 neurons. So you don't have a problem here at the input layer. The problem will be at the output layer, right? Because the output layer in image captioning, you will have a sequence and every sequence will have a different length. So I don't know how many neurons should I keep here so that I can solve this problem, right? Similarly, if you are doing sentiment classification problem, then the input is actually a sequence, right? So you don't have any problem at the output, it is okay, but the problem would be at the input layer, that how you actually feed data or sequential data to this ANN, right? So now we'll be moving to RNNs, right? But before looking at the technical details of RNN, right? There's a very good hypothetical study, which is not completely true, but it is a very good example to develop the basic understanding of RNNs, right? I have given the link. There's also a YouTube video, which is exactly on the same example, right? But the video is actually quite long. So I have taken, you can say, some small parts from that and compiled some slides. So it is actually a very good example if you are looking at RNNs for the first time, right? Because this is slightly different from whatever we see in machine learning, because when you see CNN, it is actually an extension of ANN, right? It is not totally a different world. But when we are migrating from CNN to RNN, now we are in a different world, right? We are in a different world. So that's why it can be slightly challenging to understand for the first time, but this is a very good example. Okay, if you don't understand from this short example, you can see the complete video on the YouTube, which will actually help you understand this, right? So they have taken this example of cooking, right? Where they say, okay, you have a chef at home which actually cooks three different types of dishes, right? And what are those dishes? Maybe dish number one is an apple pie, then a burger and a chicken, right? So it's not a perfect example for the month of Ramadan, but unfortunately, we have this example, so please be with it, right? So initially, we keep our things very simple, right? We say, okay, this chef is actually fond of patterns, so whenever he has to take a decision, he will see some pattern and make the decision that what has to be cooked. Okay, so initially, we keep our model very simple. We say, okay, basically, the chef is looking at the weather. Okay, so whenever the weather is sunny, the dish would be an apple pie, and whenever it is rainy, okay, so maybe he's going for a burger, right? Now let's model this problem using numbers. It's very simple problem, okay? No RNN, no nothing. It's fairly simple. Since we have three dishes, so we have this one hot representation for three dishes. We have two states of weather. So a vector of two, 1, 0 is sunny and 0, 1 is rainy, right? Now you can make a model, a simple feed forward neural network, that once you feed sunny or 1, 0, you want this as an output. And once you feed rainy, that is 0, 1, you want this vector as an output, right? So since it's a very simple problem, you can actually with hit and trial, ideally it should be through learning, but since it's a very simple problem, so you can learn the weight matrix, which is like this, okay? It is a binary weight matrix. You just assume we got it from somewhere, okay? We are not going into the details of the training. Now this is our weight matrix. If I multiply this matrix with the vector for sunny, I get this vector, which I wanted. Similarly, if I multiply this weight matrix by input, which is rainy, I get this vector and which is I wanted, right? So you have a weight matrix which is mapping this weather to this dish and this rainy to this dish, okay? And if you want to visualize it, right? So this is your neural network. You have a vector of input 2 here, like 1, 0, and you have 3 neurons because the dish is represented by a vector of 3, okay? Since we had a binary weight matrix, so everything which is 1 is connected and everything which is 0 is represented by a dotted or a dim connection, right? So you can actually feed 1, 0 or 0, 1 and you can verify that this works perfectly fine, okay? So this was our first, you can say, hypothetical case study in which no memory is required, nothing is required. It is a conventional feed forward network, and that too very, very simple. Now let's add some more, you can say, detail to this example, right? We say, okay, now cooking is not based on weather. Okay, the mood has changed, and now the chef has decided that I will cook dishes in a sequence. Okay. And what is the sequence? That he has a predefined sequence that, for example, if Monday it was an apple pie, then the next day is a burger, and then you have the third dish. Okay. So you see, you have cooked every dish. After that, you go back to the first dish. Okay. So he will keep on cooking in a sequence. Now, since we have sequential data, so in a sequential data, we cannot use a conventional, you can say, feed-forward network. Now we'll have to design a recurrent neural network. Okay. So what is it? Let's keep it a black box. Okay. So I'm not opening this box for the time being. What is important is that suppose on Monday, this dish was cooked, right? Which was an apple pie. Just ignore this arrow for the time being. Okay. We're not talking about this arrow. If you want to predict for Tuesday, what you need to do, whatever you cooked on Monday, this should go back as an input, right? Because this will now decide that if the previous dish was an apple pie, the next dish should be a burger. Now, if I ask you what is cooked on Wednesday, so you will feed this as an input, which is burger, and it will predict the next dish. So now you see what is actually happening. If you write it technically, your output at time t minus 1 becomes input at time t. Okay, so for example, first Monday, this was the dish we want to predict for Tuesday. So we get this prediction. Now, if I ask you what is for Wednesday, you will again feed this as an input, you will predict this. I ask you what is on Thursday. So you will feed this as an input and you will predict this. So you can do it as many times as you like. So important thing is that what is your output at t minus 1? It becomes input at t. Okay, so instead of this, which is a unfolded representation, in many books, in many slides and literature, you will see RNN represented by a loop like this. Okay, some cases you will see this loop. Okay, so this loop is actually telling you that whatever output you are getting at t minus 1, it is fed back to the same model at the next time step, which is t. So this loop is actually a delay of one time step, right? You predict and then you feed it at the next time step, right? Not instantly, right? So this is actually delayed by one time step, right? Now, just to develop some more understanding, you see, suppose you are absent from home for a few days. Okay, you are not there, and you come back after 2 days, and you are trying to predict. Okay, when you left, this was cooked. You were absent for 2 days, and now you come back. You still can do the prediction by backtracking. Okay, you can go back. Okay, I left on maybe Thursday. This was the dish, so you can predict what is here. Then you can feed it here. You can predict, and you can keep on doing it as many times as you like, and then you can get the desired answer. Okay, so now if we want to model this, you can say until now, of course it is not complete yet, but if we want to model this by numbers, so we say again we need a matrix which can map one dish to another dish. Okay, so you need a matrix that if you give this vector as an input, you multiply by the weights, you should get this, right? Similarly, if you are going this as an input, we want this as an output, and so on. Okay, so since again it's a small data, so we can assume that someone told us that this is the matrix. Okay, so these are weight matrix. You can multiply this with the dish, you will get the next dish on the sequence, right? So we can represent this by a network like this, where we have 3 neurons here and 3 neurons here. Why 3? Because input is a dish, output is also a dish, and dish is represented by a vector. Okay, but what is new here? New here is this loop. Okay, that you can run it as many times as you like. Okay, now you have this weight matrix. Maybe you can represent it by these connection. You keep in on running it maybe 10 times or 100 times. So you will be able to predict whatever is missing, or you want to unfold it maybe n number of time steps. So you can do it. You just need to compute one output and feed it back as an input, right? Okay, so now we are in a position to slightly add more detail to this. Okay, and this will allow us to be relatively closer to how RNNs actually work. So far, we had been quite far. Okay, now we say, okay, The chef is still cooking in the sequence, but now he also takes an additional parameter into account, that is weather. Okay, so he has a defined sequence and he says, okay, if the weather is sunny, he will use the same dish as yesterday, right? Maybe it's sunny, so he doesn't want to cook, he wants to go out and enjoy the sun, so he will say, okay, the same dish from yesterday will be used. And if it's rainy, so he has nothing much to do, he will say, okay, I will pick my next dish on the sequence, right? The sequence is already there, right? But whether he is going to pick from the sequence or he is going to maintain the previous dish, it is dictated by the weather. So it is something like that. Okay, if it is sunny and previous day this dish was cooked, so today we expect the same dish. On the other hand, on Tuesday we had this, but the weather was rainy. So the next dish we expect is basically the next dish in the sequence. You already have that defined sequence. The only thing that has changed here, that now you have an additional input coming from this arrow. Previously we did not have this input. Now we have this additional input, and if this input is sunny, you keep the previous one, and if this input is rainy, you actually move to the next dish in your sequence. So now this is relatively closer to how you can say an RNN works in practice, right? So this was the situation at day t minus 1. Okay, you cook this thing. Now when you are predicting for day t, you will say, okay, what is the weather on day t? So this is your input at day t, and you will say, okay, what I cooked yesterday was this, so now this was the output of day t minus 1. For day t, now this will become the input. Okay, so this is your model. One input is coming from t minus 1 and one input is coming from t, which is actually the weather, and you are predicting this output for day t. Okay, so now you see this terminology, it looks relatively close, that you have an input which is coming from previous time step, you have an input which is coming from the current time, which is t, which is weather in this case, and using these two pieces of information, you are making a prediction for the dish on day t. Okay, now of course these next few slides, they are not much realistic, but still if we want to implement it with some hypothetical this hypothetical example with some network, right? So we can also do that, right? Now you have the dishes represented by vectors of size 3. You have weather represented by vectors of 2. Okay. Now you will need a matrix for food, okay, and a separate matrix for the weather. And you have to combine these two pieces of information, which we are calling merge, so that you come up with the final decision. Okay. So now you see someone told us that, okay, for the food, this is your weight matrix. Okay. How it is learned, we just ignore it. Now you see what will happen if I'm using this weight matrix. If I multiply this matrix by my first dish, I get two options. Okay, we get one big vector of 6, but logically these are, I can split it into two parts. So you see this first part is actually giving me the same dish which was input, and the second part is giving me the next dish on the list. And this is true for each of the three. If I multiply the same matrix with this dish, you see the first part, the first three values are suggesting me to keep the same dish, and the next three values are suggesting me to pick the next dish. And same is true here. Same, next. Okay, so it means that the food matrix has given you two options. Either keep the same thing or pick the next thing. This is what we wanted. Now let's see what is going on in the weather matrix. This is the weather matrix. If I multiply it by sunny, I get this as an output. Now you see we have three ones in the top part and zeros in the bottom part. So you can guess that it is suggesting maybe we keep this part. Okay, this could be a suggestion. You can actually link the two. Similarly, if I multiply the weather matrix with rainy, I get this vector as an output where I have zeros in the top part and ones in the bottom part, which could be a suggestion that pick the lower part of this matrix. Okay, so as I told you, this is just a very simple example. Practically it would be much complex than that. So it means we need to add these two pieces of information somehow, right? And we will be able to actually have something meaningful. Okay, so now let's apply this to a scenario where the previous dish was an apple pie and it is raining today. Okay, so what will happen? So basically we get this as an output and we get this as an output. Okay, because we are assuming the first scenario that the previous dish was an apple pie. It's sorry, it's raining today, so we are taking this example. Okay, so now this is the output we are getting from the food matrix, and this is the output we are getting from the weather matrix. Okay, so we simply added them. Maybe we get this. You say, okay, I want binary numbers only, so maybe I'll apply a non-linear transformation which will give me 1 at the highest value and rest everything is 0. So maybe we can apply some transformation to get something like this. Okay, and then we say, okay, let's ignore the 0 part, only keep this which has some meaningful part. Okay, if you keep this, you get this as an answer, and this should actually be your answer, right? Because it was ready and the previous dish was an apple pie, so the next dish should be a burger. Okay, and you can actually implement it by connections like these. Okay, you can actually do a forward pass and convince yourself, right, that I'll not be doing it the complete flow, but you can actually convince yourself that, okay, when I feed this as food, this as weather, so this is actually your food matrix, this is your weather matrix, you will get these outputs which I showed you on the previous slide. Then we added them together, we get this. Okay, and finally we apply a nonlinear transformation so that we only keep the maximum value, so we get this. And then somehow we can merge these pieces, map this vector of 6 to a vector of 3, so we'll get the desired output here. Okay, so you see, since it was a simple example, but still all the key components of RNN have been discussed here. So actually these matrices, of course, will not be random or not be guessed. They will be learned through back propagation, right? And once you have this model, what is important is that whatever output you are getting, you feed it back here. Okay, because food is what you are feeding back, not weather. Weather has a new value for every day, but for food, you need information from t minus 1. Okay, so the loop you see here, this information is coming from the previous day and the weather is coming from today, right? So this is previous day and this is today. Means there's a delay of 1 timestamp, right? So as I told you that it was a simple problem, so the weights were actually guessed by the author of this tutorial, right? But actually you have to you can have these weights as parameters and you can learn this, right? Okay, so now with this hypothetical example, which actually tries to, you can say, give you some idea of how RNNs work. So now maybe we can go back to our technical part, right? And now when we study RNNs, then you can always correlate it with the information that we had seen. So it will be easier for you to understand, right? Okay, now before going to the details of RNN, there is some information about that, you can say visuals that you will see not only in the slides, but also in different tutorials or something like that. Okay, so this is very important, that because otherwise when you will study some tutorial or watch a video, they will directly show you an illustration of RNN, which can be confusing for you, right? So it is important to understand why we have that notation when we are visually representing an RNN. Okay, now for some time, let's forget about ANN. Okay, sorry, let's forget about RNN, just focus on a simple ANN, right? So on your screen, you can see a simple ANN. These are different neurons and every neuron has a single value, right? Maybe 1.56. So every neuron has a scalar value. Okay. So what we can do is this complete layer, it can be represented by a vector, say V1. Okay. You are doing actually encapsulation, that you are encapsulating this complete layer by a vector, and you represent this complete layer by a vector of 5, and I just make one single neuron like this. Similarly, this complete layer can be encapsulated by a vector of 3, and you can represent it in this form. Okay, and this is already a single value, so you represent it like this. So you can represent your complete neural network, a conventional feed-forward network, by in an encapsulated form like this. So this is not a one neuron now. Okay, these are 5 neurons. This is a vector. Similarly, these are 3 neurons, and these are this is 1 neuron. Okay, and why we are doing it? Because when we are visually drawing a network for a recurrent neural network, we will have sequential data. We'll also have a time axis. So if every time you draw this complete architecture, it will be very confusing for you, right? Because you also have an axis which is called the time axis. So that's why in almost all the literature that you will see, when you see RNN, you will see this compact representation, right? So many students in the previous batches, once they actually went through those tutorials, so they were not able to understand that why every example is with a single neuron. The point is that this is not a single neuron. This is an encapsulated representation of a neural network where each neuron is representing a complete vector. And in other words, this one circle is representing one layer. Okay, so please do remember. And another additional thing that we'll do is that we will rotate this by 90 degrees. So it will become something like this, sorry, something like this. Okay, it's the same thing, that input, hidden, output. So I have rotated this diagram by 90 degrees. So now this is my input, this is the hidden layer, and this is the output layer. Okay, so with the RNNs, we'll be drawing something like this: input, hidden, output. Okay, but this is not one neuron. These are not three neurons. You have five here, sorry, five neurons in the first layer, three in the next layer, and one neuron in the last layer. Okay, now with this preamble, we discuss, you have already seen different applications or case studies. I'll show you again each of these, but this time we will see what type of RNN we will require to solve this problem. Okay, now let's see the first one and then we discuss further. So a little while back we talked about this image captioning problem. Okay, it is called one-to-many mapping. Why one-to-many? Because input is an image, which is a single input, so we are calling it one. Output is a sequence of word, right? So for sequence, we use the term many. Okay, so image captioning is an example of one-to-many mapping because you have one input and a sequence as an output. Okay, now if I want to draw visually that, okay, what type of architecture I will have to solve this problem. Now this is very important, right? So I would need your attention. Now you see on this axis we have time. Okay, what you see in red, what is this? This is not a single neuron. This is the input layer. So if your image is 10 by 10, it means there are 100 neurons here. Okay, so this red is actually one layer of a network. Like these could be 100 neurons. This is the input layer. Okay, this is your hidden layer. How many neurons are here? You choose maybe 5, 10, anything, right? And this green is your output layer. Okay, now suppose there's there's an image and the caption is a cat sitting. Okay, so it means you have three words. So the first output would be a, second output would be cat, and the third output would be sitting. And if you are representing these words by one hot vectors and there are 100 words in your vocabulary, so you see this is actually, these are 100 neurons here. 100 neurons. Why? Because you have a vocabulary of 100, so you have to pick one word out of 100. Now actually your architecture was like this. Okay, when you see this axis, you are unfolding the architecture as many times as the number of words you require in your output. Okay, so now you see what is happening. If my output has three words, I will unfold it three times, so it will say a cat sitting. Suppose it says a cat sitting on a chair, so it will have one more time step, another time step, and for every time step it will give you an output. So you see, this is something very useful. We can, if I have 5 words or 10 words or 3 words, I have to repeat the same process. Okay, and of course there will be an end of string token which will tell me that now I should stop. So on the on this vertical axis you have depth of the network, means you have layers, input, hidden, and output. And on the horizontal axis you have actually the time. Okay, you have actually timestamp, that first word, second word, third word. So if you have 3 words, we are calling it 3 time steps, 1 to 3 or 0 1 2, whatever convention you are using. So the first one is an example of one to many, where input is a single image, output is a sequence. Okay, now let's see another example, which is the reverse case, which is many to one. Now what is many to one? We had done this example, sentiment analysis, right? If I say food was good. Now you see input is a sequence. You are feeding the first word, second word, third word. This is your hidden layer, and this is your output layer, which is a single neuron, maybe you are saying whether the review is positive or negative. So you can use sigmoid activation function. So when you feed the complete sequence, only then you can take the decision. Okay, you cannot take a decision by looking only at the first word. You see the feed the first word, second word, third word, and once the complete sentence has been fed, now your model can take a decision that whether it was a positive review or it was a negative review. So this is an example of what we call many to one mapping, because input is a sequence and output is a single value, which is the class label. Okay, now the generalized form, which is called many to many mapping, right? And the classical example is language translation, where input is a sequence. So you feed maybe 3 words, right? And you expect the translation in another language. Now you see in all the examples, this blue is actually showing us the hidden layer. So in all the previous example, we are only using one hidden layer, because on this axis you have depth. It is perfectly possible to have 2 hidden layers, right? So this is your hidden layer 1 and 2, right? First hidden layer and the second hidden layer. So on this axis you have depth. This red is your input layer and this green is your output layer. But here both input and output are actually sequences. So it is called a many to many mapping because both are sequences, right? Now let's sum up all of this discussion. This is a very good table, right, which is available in an online course. So it actually sums up all the possible scenarios with one example application of each, right? So you see, if you talk of one-to-one, means input is a single value, output is a single value, then we are talking about traditional neural network, right? Input is an image, right? And output is a label, which is cat. So you don't have sequence neither at the input nor at the output. So this is actually not an RNN. This is the conventional ANN or CNN, which can solve this problem. Okay. Next, you have one-to-many problem, right? You give one input and the output is actually a sequence. So for example, you give that I want to generate music of this type. So you give one single input and the output is a sequence, which is actually the music that has been produced by the model, right? So this could be an example of one to many. Many to one, we just discussed. The input is a sequence of word. These are sequences. And this output is actually the class label. So sentiment classification is a very good example of many to one mapping. In many to many mapping, you have two possibilities. One possibility is you feed a sequence, output is a sequence, both have same length. Tx is actually the length of the sequence. So Tx equals Ty means input and output have same length. A perfect example is named entity recognition, right? You feed a sentence and for every word you have to say it is name of a person or not, right? So you will have a vector of zeros and ones where you will get a 1 at the position where name of a person is appearing, right? So in this case, it is a many to many mapping, but relatively easier because the length of input sequence and the length of output sequence, they are the same. Now, a very generalized and the most challenging part is a sequence to sequence problem where input and outputs are having different lengths, right? So this is a sentence in French and the output is a sentence in English. So this machine translation is an example where the length of input and output can be different. So out of these examples, let's focus on this example, which is named entity recognition, to further develop some ideas, right? So this is basically a concrete example, right? So we have a text, maybe a sentence. Jeff Hinton and his team introduced capsule networks, right? So this is the input sentence. So our unit is a word. So X1 means first word, X2 means second word, Tth word, and there are total 9 words in this sequence. For every word, we have a label, which is represented by the symbol Y. 1, 2, 3 in angle brackets, they are referring to the timestamp or word number 1, word number 2, and so on, right? So we were having names of people here. So the output is 1 here. And we did not have any other name of an individual. So the output are 0. So the length of input, we use the symbol Tx, which is 9 in this case, and output is also 9. Of course, if there is another sentence, it may have 6 words. So output will also be a vector of 6. But the important point is that for a given example, input and output will have the same sizes. Now, as I told you, we'll not have one training example, we'll have multiple training example, right? So we use this symbol I, right, xi for the ith training example, and this angle bracket t, this is referring to the word number or the timestamp, right? So if we have, say, maybe this word, so this is x2, because this is the second training example, this is 2, and in angle bracket it is 3 because it is the third word of the second training example, right? And same convention will follow for y, which are the labels. The length of training example can be different, so that's why we have the superscript I, which is giving you the length of training example of the ith training example, right? Similarly, you will have the same for y as well. Okay, now assume that for the time being, we are not going to word embedding. We'll go to word embedding in a while. We have a dictionary of 10,000 words, so we represent all the words using one hot vectors, right? And normally when we are implementing things, so you see at test time, it is also possible that you get a word which was not present in the training data. Okay, so we don't want our system to crash because it will have an unexpected input. So if you have 10,000 words in the dictionary, you add an additional token which is called unknown, right? Unknown means that it is very much possible that at the testing you find something which was not present in the training data. So what to do at that time, right? So it is just a implementation note. Okay. So now you see, again, let's try to solve this named entity recognition problem using a conventional ANN, right? So what will happen? We'll feed the first word, second word, and you can say the ninth word. As we discussed earlier, there are 9 inputs, so there are 9 outputs, okay? But the second training example can have, say, 10 words, another can have 12 words, another can have 6 words. So still, you see, it is not a very serious problem because we can solve this problem using padding. What we can do, we can say, okay, the maximum sentence can be 50 words. So here we can have something which is able to handle 50 words. And if you have less than 50 words, you pad zeros here, and also you ignore the output neurons in that case. Okay. So I think this length problem can partially be solved using padding. But the more serious problem is basically the sharing of features which are learned. For example, when we say Jeffrey Hinton, so you are feeding Jeffrey Hinton on neuron 1 and 2. Okay, someone else actually rephrase this and maybe write it in passive voice, right? That capsule networks were introduced by Jeffrey Hinton and his team. So now these two words will be coming somewhere here, okay, because you have changed the order of the words. Now you see, when you are learning the weights which you are learning here and here, so you see position is important. If these words are changing position and they mean the same thing, then this information cannot be exploited by this conventional ANN, right? Because then it is actually learning that, okay, this word appeared at this particular position, which we don't want. So to solve all of these, now we'll be designing our first RNN. So maybe I'll do it very slowly on the board so that you get the idea to actually solve this problem, which is named entity recognition, right? So we'll have a sentence, maybe say, this is our sentence. Okay, I'll not write it complete and I'll just write it like this. And presently you can assume that we are not using word embedding. We are representing every word via vector. Okay. So we'll read the sentence from left to right and we'll feed it to a network. Okay. So first decide, we have an input, we have an output, and we have a hidden layer. Okay. So this is our input. And when I write x1, I am talking about the first word. Okay, let me just rather correlate it. So this x1 is actually the first word. And how am I feeding it? Here I actually have one hot representation of this, which is actually fed to the hidden layer. Okay. So anyways, now let's say we decide on one hidden layer and we say, okay, how many neurons I will have in this hidden layer? Let's say I have, say, 4 neurons, 3, 4. Okay, so you are feeding this first word to this neuron, okay, and you are making a prediction for this let's call it y hat 1, that whether it is name of a person or not. Okay, we feed the first word, and for the first word we expect a prediction. Now when we feed it the second word to the network, what is the second word? Second word is x2, and what was that word? That word is actually Hinton. Okay, and we want to predict whether it is name of a person or not. Okay, but now instead of taking the decision only by looking at this input, we say, okay, let's also get some input from the previous timestamp. So this arrow is very critical. Now, what is this arrow? I explain it in detail because this is the whole idea, that you see, you are making the first prediction, you get some output. When you are making the second prediction, you are looking at this input, which is at time t, which is like weather. But you also see what was happening at t minus 1. Okay, so you are getting something from here, which is like the dish you cooked yesterday. Now you can relate that example with this one. You have a current input, which is Hinton, and you are also getting some information from the previous time step, because that could also be useful. So you are getting something from t minus 1. And what are you actually getting? You are actually getting, you see, what is this actually? This is just like a layer of a neural network, just drawn differently. And 4 neurons here. Okay, you have input, you take the dot product, so you have some activation which is going out. So here you have the output of this hidden layer, which we are calling activation, or we are representing it by A1. Okay, and the same thing is going here actually. So you see, I have taken 2 branches from this. One is going to Y, and the next one, this branch, which is horizontal one, this is going to the next time step. Okay, so this slightly tricky, I understand, right? But with some more, you can say, discussion, I hope it will be clear to you that now this is our hidden layer. This is the output of this hidden layer, and of course, it is going to the output layer, which is Y. And the same thing, right? It is the same thing. We are also feeding to the next time step, not next layer. Okay, this is the same architecture, but now on this axis we have time. So maybe let me draw it a bit cleanly so that you can understand, right? So this is our hidden layer. Okay, this is our input layer. So I feed the first word. Okay, and this is the output of hidden layer, and then I have the output layer in which I am predicting whether it is name of a person or not. So I'm predicting basically 1 or 0. And this is my, you can say, second input. It is exactly the same thing. I am feeding the second word. Okay, I am getting some output or activation of this layer, and I am making the prediction for the second word. But now in making this prediction, whatever was going here, okay, you can actually bring it from here if you feel strange, or in notation normally we bring it from here, it means the same thing. We are also getting the information that, okay, what was the activation at the previous time step. Similarly, when you are predicting for the third word, okay, so you are feeding the third word, you are getting some activation of this hidden layer, and you are making this prediction. And this is 3. And here again, you are getting the input from the previous timestamp. So this is t, right? This is t minus 1. This is t minus 2. So you see, it's the same thing. X is like weather, and the arrow which is coming from the previous timestamp, it is like, you can say, the dish which you cooked yesterday. Okay, and you see, you can do it as many times. For example, if I am feeding 9 words, I have to draw it 9 times. Okay, so normally in the literature, rather than doing it like this, okay, you will see a compact representation of this, which is like this. Okay, that you have xt here, and you have at here, which is actually predicting yt, and instead of drawing it 9 times or 10 times, you just put this loop. But do remember, this loop is actually a delay of 1 timestamp, right? Because whatever you predicted, at the next time step it will become input. So when you see this loop, it is actually, you can say, a delay of this 1 time step, right? So before moving further, let me just show you the same discussion, maybe a cleaner version on the slides, right? Okay, so maybe it would be easier for you to get the idea. Again, a repetition of the same thing, but slightly neater version of the same concept. So we are reading the sentence from left to right. Okay, we read the first word, we feed it to the neural network, all right, and we try to predict the output. So this was the first word, we feed it to the hidden layer, this is the output, and then we have basically 1 or 0, which is the output. Now, when you need to read the next word, which is x2, so rather than directly predicting the output by looking at x2, you also get some information from the previous time step, which is the activation of the hidden layer, right? So this A1 is coming here. This A1 was also going to the output layer, okay? So it means you are using this information from the previous time step. Similarly, you can repeat the same idea for x3, x4, and so on. So we can say that at any given point in time, you are exploiting the information from the previous time step and the current time step, and you are making the current prediction, right? So as I told you that since you have to unfold it many times, but initially when you are learning, it's a good idea to unfold, right? Because if you directly see this compact representation, it is not very intuitive. It may be difficult for you to understand, right? So in the beginning, maybe you can prefer this notation. But later on, when you are writing a report or a thesis, then of course this rather than this, you can use the compact representation. Okay. Now, another you can say minor comment is that you see all the you can say all the predictions are getting something from the previous time step. But when you feed the first word, there is nothing here. Okay, because there is nothing before the first word. But in order to make our expressions consistent, right, what we do is we introduce a0, which is a vector of all zeros. Okay, because there is nothing coming from here. But the advantage of using a0 is that now when we will be writing the equations for this, we will have a consistent notation. Otherwise, if we are not using this, you can say vector of a zeros, then the problem would be that we'll have to write a separate expression for the first word, and for the subsequent words we'll have a separate expression. We want to write one single expression which is valid for everything, right? So this is why we'll be using this notation. Okay, now the perspective of you can say computations, you see actually, as I told you, if you have 4 neurons here and you have 10 neurons here, so actually this arrow is just like a connection in a simple feed forward network. So this is the dot product. Okay, so you will have a matrix here, the size of the matrix would be 4 cross 10, and you will be multiplying weights with the inputs, applying some activation function, and then you will be computing these 4 values. Okay, so please don't think what is this arrow. This arrow is just like the connections that you have in a conventional feed forward network, and you have a weight matrix. The size of the matrix depends on how many neurons you have in the hidden layer and the input layer. For example, 4 in the hidden, 10 in the input, so your matrix is 4 cross 10. You take the dot product, apply some activation function, and get the 4 values, right? The the most important part in all of this discussion is that when you are feeding the first word, second word, third word, this weight matrix actually does not change. The most important is that at all the timestamps, the same weight matrix is used, and it does make sense, right? Why is it so? Let's see this in slightly more detail of this. That you see, when I am feeding this data, sometimes I will have 3 words. Sometimes I will have 5 words or 50 words or 20 words. So the length of the sequence can be anything. So it is not possible that for 50 words I learn 50 matrices. When I have 5 words, I learn only 5 matrices, right? So the weight matrix you have, it is exactly the same, means the weight matrix you have here, here, here. So all the timestamp, because on this axis you have time, exactly the same weight matrix is used, and that's the way it should be. Because if it is not like that, then it means that for every timestamp you will have you can say a different weight matrix, and learning would not be possible in that framework, right? So let's go back and see something, some more details. Okay, so far what we have seen, so far we have seen that in an RNN, when you are making predictions, you are looking at the current information and exploiting the past information to predict the output. Okay, but in some cases, past information may not be sufficient, and future information can also be helpful. Okay, what do I mean by future information? I tell you in the next slide. Okay, now let's see this pair, this first pair of, you can say, text. Okay, so the sentence is, he told us that Paris, and he told us that Paris, but we don't know what is ahead. Okay, so Paris can be name of a city, or Paris can be name of a person, right? But by looking at the past information, which is the previous words, you cannot take a decision on the current word, right? Because it is ambiguous. Another very good example, which you find in different tutorials, he said Teddy. Now Teddy can be name of a person, and Teddy is like teddy bear as well. So we don't know whether we are talking about a person or we are talking about a teddy bear just by looking at the past information. But if somehow we are able to see the complete sentence, means I am able to see in the future that complete sentence. So now you see, it is very easy for me. He told us that Paris Hilton is the great granddaughter of Conrad Hilton. Now I can say, okay, here we are talking about name of a person, because I was able to see this part. Similarly, he told us that Paris is likely to receive more snow in this winter. So it is very easy for me to say that here we are talking about the city. Okay, so you see, this was past information, this is future information. The term future can be misleading, right? Because we can't see future. Future means that whatever is coming next. So since your complete training data will be available, this complete example is available. So by future data, you mean that rather than scanning from left to right, you can also scan it from right to left. Okay, so this is what we mean that by you can look at the future information in advance. Likewise, for this example, Teddy Roosevelt was a president, teddy bears are on sale, right? So you see, when you see this part of the sentence, it's very easy for you to guess that here we are talking about a person, and the second sentence, we are talking about a teddy bear, right? So the idea of these informations is that future information can be used, right? So for the time being, we'll be only talking about past information, but once we have a basic understanding of RNN, will be using something which is called a bidirectional RNN. Okay, or in short, it is called a BRNN. So a bidirectional RNN is simply basically you can say not only you look at the past information, but you also look at the future information. Okay, so now maybe we have around 10 minutes, so maybe I can just go back to the discussion of RNN and we can add more details to our discussion. Okay, because or maybe I can show you a clean version on the slide and I can write on the slides. Okay, so this way, yeah, here we can write. You see, so far we did not talk about explicitly much about weight matrices, activation function, or I did not write any expression so far. We have just been telling some stories, right? So now is the time that, okay, let's try to write some expression. Okay, that what is this A1? How do you compute this A1? Okay, means A1 is the output of the hidden layer. So you see, basically, you have input coming from here. Every arrow is a weight matrix. So for example, I call this weight matrix as AX. Okay, so this arrow is actually not a single arrow, as we discussed. If you have 3 neurons and 2 neurons, so these are actually 6 connections. Okay, we are representing it by a single arrow. So this arrow is actually a weight matrix. Similarly, you also have an arrow here. You see this on this horizontal axis. So there's also a weight matrix here. What are the sizes of these matrices? Maybe we don't discuss, I tell you, but we'll discuss in detail at a later stage. Input is easy to guess. If the input is 10 and you have 4 neurons in the hidden layer, so this is 4 by 10. So can you guess what would be the size of the weight matrix which is here on this horizontal arrow? 4 neurons here, 4 here. So actually the size would be 4 cross 4, right? Because you have 4 neurons here, 4 neurons here, and you are connecting all of these. We are representing it by a single arrow, but actually everything is connected to everything. So 4 into 4 is 16, so the size is 16. If you don't get it, just ignore the size for the time being. I'll have a detailed discussion on sizes later on. For the time being, just let's focus on the matrices. Okay. Okay, so let's ignore this. We talk about this one. Okay. So now how A1 is computed? Input is multiplied by input matrix. Okay, so we say maybe WAX is multiplied by X1. Okay, so we are done with this part. Then another thing is coming in this hidden layer from the left side. What is happening? A0 is multiplied with WA. So this weight matrix is multiplied with A0. You also have a bias. You have 4 neurons, so you will have a bias vector which will have 4 values. So I call it BA. Okay, so these are actually a vector of 4. So you see, this is what is happening in the hidden layer. But don't forget, we do this and then we apply some activation function. Okay, so previously in a you can say regular network, we just had this part and this part. Okay, current input, bias, activation function, you get the output. Now you have a new term. You see, when I am computing for timestamp 1, I am using information from timestamp 0. So this is actually the past information, or you can say the t minus 1 information. Okay. Okay, so we have written it for A1. Similarly, you can write it for A2. What would be A2? I just change it to 2 because you have this input multiplied by the same weight matrix. Similarly, you have this A1 coming, so this will become 1 multiplied by the same weight matrix, and you will have a vector of 4, which are the bias values, and you will apply the activation function. So you see, the same expression works for every timestamp. You just have to write it for AT. Okay, so if you write it for AT, you can just replace the value of t, and you can easily you can say convert it into uh, any value that you like. Okay, now let's try to write it for the output. Okay, because we have not written it for the output, that how are we computing this y1. Okay, so let me write for y1. Now what is this? This arrow again is a matrix, weight matrix, and what is coming on this A1 is coming. Okay, so if you want to write for y1, so let's say the weight matrix here, let's call it WYA. So what are we doing here? WYA. Okay, this is multiplied by A1, which is coming from the hidden layer, and of course you will add some bias, let's call it bias, and you apply some activation function, so you get this y. Okay, now you see again in this there is no past information for computation of y. You are just using the activation of the hidden layer and you are computing the output, right? So these expressions are here, right? I'll show you on the next slide as well. So normally in RNN, the hidden layers will be using tan-h activation function. Okay, and the output layer, mostly they will be using either sigmoid or softmax, depending upon whether you are solving a 2-class problem or a 1-class problem. Okay, now if in the clean form I show you the generalized form of these expression, so you see rather than 1 2 3, now we can write a generalized expression for AT. So AT means you are talking about A1 2 or anything. It is this input at current timestamp, which is xt, multiplied by this weight matrix, which is on this arrow. Okay, WAX is on this arrow. All of these arrows have the same weight matrix. Plus, what you are doing, you are picking the activation of the previous timestamp, which is t minus 1, and on all of these horizontal arrows, you have a weight matrix, which is WAA. So you are multiplying it with this, adding bias, and then you get the activation, which is the output of the hidden layer. Likewise, for the output layer, what do? We have this, you can say, a weight matrix on this arrow, right, which we call WYA. So in computation of output, you are actually looking at the current input. Sorry, by input I mean the output of the hidden layer and the bias, and you are applying the activation function. Okay. Now one last thing for today, as I told you, let's discuss the size of these weight matrices. So you see, when I'm writing X or Y, so actually I'm not drawing this all the time, but X is something like this. Okay, if it's a one hot representation, maybe there are 10,000 neurons. Or for this example, input is a 10-dimensional vector. So when I write x1, actually it is like this. Okay, hidden layer, I already draw 4 neuron, and the output, for example, if you are solving a 3-class problem, you will have 3 neurons here. If you are solving a 2-class problem, sentiment analysis, then a single neuron, which is 1 or 0. So now you see what is happening. You have 4 neurons here, and 10 neurons here. Just look at it from the perspective of ANN. Okay, so everything in layer L minus 1 is connected to everything in layer L. So the weight matrix is 4 cross 10. There are 40 weights. So that's why this weight matrix is 4 cross 10. Okay. Similarly, after these 4 neurons, if I have a single neuron, okay, so how many connections I have? 4 connections. Okay, so the weight matrix is 4 cross 1. Okay, it is only rotated like at 90 degrees. Otherwise, if you rotate it back, if you rotate this part back, okay, what will happen? It will be like 10 neurons, then you have 4 neurons and a single neuron. So you have a matrix of 4 cross 10, and then you have a matrix of 4 cross 1, sorry, right? And here you have 4 cross 1. The only new part is that this hidden layer is connected to the next hidden layer. By next, I means at the next time step. If this was t minus 1, this is t. So you see, here you have 4 neurons. So in the next time step, you again have 4 neurons. The hit size of the hidden layer is not changing. So that's why on all of these horizontal arrows, if your hidden layer has 4 neurons, WAA will be 4 cross 4. If it has 40 neurons, WAA will be 40 cross 40, right? So with that discussion, I'll stop for today, right? It's a slightly challenging part, so I'll stop here, and we'll see more of RNNs in the next lecture, right? So before we conclude, if you have any questions, which you normally don't have any, right? So you are welcome to ask.